I'm Laurissa Smith, and I'll be chairing this next session that'll make you think differently about food by harnessing satellite technology. In this session, we explore how satellite Earth observation can revolutionise agriculture by providing farmers with precise real-time data. We'll also look at the innovative collaboration between UK and Australian Earth observation scientists, and shortly you'll get some insights from Dr Hugh Mortimer. Then our panel of experts from the UK and Australia will delve into how space technologies can shape a more resilient and sustainable future for ag, underpinned by climate, food security, biosecurity and water resources. And then we'll have a Q&A session, so keep those questions coming in as well. You can also continue this conversation online on your socials with the hashtag ABARESOutlook. Now I'd like to introduce physicist and science communicator Dr Hugh Mortimer. He has a wealth of knowledge when it comes to Earth observation technologies in the UK and abroad, and he's going to tell us a bit more about the Australia-UK Collaborative Research Program on Satellite Earth Observation for Agriculture and Climate. Thank you, Hugh.
Thanks, Laurissa. As Laurissa introduced us, we're really going to take you through some of the introduction of how Earth observation is being used to address some of the agricultural challenges, and also how we're using those to overcome some of the resilient opportunities of climate change. So, as Laurissa mentioned, my name is Hugh Mortimer. I'm Associate Director at one of our national labs in the UK for space science. It means I'm an Earth observation scientist by background and training, but because our national labs, the Rutherford Appleton Laboratory, is run and operated in a similar fashion to, I think effectively like the Australian Research Councils, I'm also in a privileged position to set up, develop and run some international programs on behalf of the UK, which is the reason I think we're all here today, and actually it's a real honour to be able to come and talk to you about how we're using Earth observation. So it's been based on this basis that I've been working over for 4 years, collaborating with CSIRO, our project partners, in delivering kind of these international programs jointly between ourselves. Before we hand over to this expert panel and start interrogating them, I wanted to give you a quick introduction to what we mean by Earth observation, because I think many people are familiar with satellite data when it comes from satellite navigation, for example, and I think we're pretty familiar with how satellite navigation is being used in tractors to do autonomous driving. It's also being used to do precision agriculture. I mean, I think everybody recognizes and probably uses it almost daily to do getting from point A to point B, Google Maps, Uber, all underpinned by satellite data. But I think people are less familiar with how Earth observation data is being used daily and impacts you on basically on a day-to-day basis. This beautiful time-lapse sequence of images that you can see on the screens, I think showcases the unique perspective that you can get if you go above Earth's atmosphere and actually look at the Earth kind of from a perspective like this. You can see the entire Earth system. You can see 4 corners of the Earth. You can see the oceans, the atmospheres, and the land. And you can do so on kind of time scales of days, weeks, months, and even years. We can do that by getting basically a satellite, launching it, bringing its speed up to about 7 kilometers every second, which means that once we're above Earth's atmosphere, we're traveling in an orbit. That means we make an orbit every 90 minutes. So this unique perspective means that we are not only able to observe the Earth on long time periods, it means we're able to do that continually. And this means that we can get huge amounts of data. In fact, this time-lapse sequence of images is taken from the International Space Station, but actually this is one of effectively 1,000 Earth observation satellites that are taking continuous monitoring of the Earth every single day. Is producing unprecedented amounts of data. Every day, I think it's estimated to be about 150 terabytes of data collected, and that's just from the NASA Earth observing system. That doesn't include the data that's being collected from private missions such as Planet Lab. But those data sets are continually being used to produce accurate things like weather forecasts. They underpin our climate data. They're also being used operationally in crop models and monitoring, enabling us to do forecasting into the future. So this really underpins some of the capabilities that we have. Once we're in orbit, though, there are some massive limitations from what we can do from space. And I think this is pretty obvious because, the satellites that we have in orbit are doing so from, well, if you're in low Earth orbit, about 300 kilometers. If you're in geostationary orbit, you're about 30,000 kilometers. And so you can imagine that a pixel on a detector of a camera in space changes its resolution. So the data that we're taking from space has limitations of spatial resolution, temporal resolution, and if you're measuring in the visible with a normal camera, if you've got clouds, and as you can see clouds there, you can't see the ground for some periods of time. So there's also massive limitations about temporal resolution. So we can't just rely on Earth observation data from space alone. We have to underpin that data with observations from the ground. And that's where local knowledge from farmers, in situ monitoring data is imperative to put context to the data that we take in space, validating and calibrating that data to ensure that we turn what is effectively numbers from a satellite, from a picture, from a pixel, into insights and information that can be used by farmers to change their practices. But that kind of global perspective that we're using satellites for is kind of underpinned by this kind of measurement. So what you can see here is a time-lapse sequence of about 40 years of data from Landsat. And these are, again, beautiful images that we can just stare at and look at because they really showcase the importance of Earth observation. But what you're seeing here is deforestation happening at on a huge scale. So I'm showing this because this is an area of land that I was working in just above that river. I was based for 3 months observing the deforestation. I was looking at biodiversity, actually. But the fact that the farmers and the local population saw scientists in their vicinity, they thought that we were there to stop them from doing their standard farming practices and their standard agricultural practices. They started to intensively deforest to turn the forest into effectively charcoal. There's complex relationships, not just at an environmental scale, but from a social scale and from kind of an anthropogenic scale. So the complex relationships you can see here from deforestation, you can see then impacting the soils, the soil moisture, the soil quality, which then goes on to the loss of this valuable resource. And you can see the soils bleeding into the oceans. And it's these kind of global impacts that Earth observation enables us to address. But on a local scale, Earth observation has a real role to play in supporting actionable information that farmers, policymakers can use to kind of make informed decisions. And it's understanding the limitations, but also the opportunities, which is where these international programs enable us to come together. So working across from the UK to Australia, it meant that we were able to set up, through international backing, through funding from our governments, a program of work that CSIRO and the Rutherford Appleton Laboratories was able to put together to fund some of these opportunities that we've identified in using Earth observation to help address agriculture and help them to become climate resilient. What you can see here is the forest fires on the west coast of Australia. The impact of climate and the feedbacks between the climate and agriculture are clear. And being able to monitor it on a global perspective means that these national programs, joined up by international activities, such as the one that we're running, can then go on and lead to potential international opportunities to address things like climate change, water security, and food security. It's a multi-billion pounds opportunity. So the economics benefits from Earth observation estimated back in 2023 to being above $266 billion US dollars. In 2030, they're expecting that to rise to $700 billion as an opportunity. So there's huge application areas, there are huge opportunities, and by addressing them on an international basis, we can start kind of addressing national and international activities. And I think that is effectively where I wanted to leave it. The last thing to say is the philosophy that we've been developing through running these international programs is effectively to bring the best researchers and businesses from the UK to work alongside the best businesses and researchers in Australia, which I think brings us neatly to the panel, which is a panel of experts that we have who I would recognize as some of the best in the world. We also have some Earth observation scientists in the audience as well, and I want to recognize the colleagues who have traveled from the UK, who have been working in partnership with the UK researchers alongside the Australian researchers to deliver some really high-impact projects ranging from monitoring methane emissions, being able to detect water quality coastally and inland, crop modeling and forecasting, and then finally being able to identify crop disease and pests and pathogens. We've got a range of expertise, we've got a range of capabilities that have been developed underneath this joint partnership. And I really want to thank all of the partners and welcome this panel session. Over to you, Laurissa.
So yes, we do. We have Professor Owen Atkin, the Director of the Australian National University's Agri-Food Innovation Institute, where he leads a team across multiple disciplines to address major challenges facing the agri-food sector. He's also a Professor of Plant Science, and a major focus of his research is assessing the impact of how the environment affects the carbon exchange process that underpins plant growth and performance. We also have Professor Richard Lucas, the Head of Earth Observation and Ecosystem Dynamics Research Group, Aberystwyth University in the UK. He has extensive experience in quantifying terrestrial and coastal ecosystems and their environments to change through Earth observation data. Professor Jadu Dash from the Department of Geography and Earth Sciences from the University of Southampton, also in the UK, specialising in remote sensing. His recent work focuses on applying satellite data to answer some of the global developmental changes in agriculture here in Australia and in other parts of the world. And finally, Dr. Phil Tickle, co-founder and managing director of agricultural data analytics company Cibo Labs, based in Toowoomba in Queensland. Phil has over 35 years' experience in the application of geospatial and remote sensing solutions focused on natural resource management, agriculture and climate change. We might start the conversation with Professor Owen Atkin. Owen, do you have some slides to go with your presentation? We'll get those ready. I might start with a question of you, Owen. How can Earth observation support decision-making across different levels of agriculture, from farmers to policymakers?
Thank you very much. It's a really great opportunity to come and talk as part of this panel today. I thought maybe what I might start off with a bit of problem definition. There's some grand challenges that we face in the sort of food system domain. One we heard just in the previous session was around inputs and the ability for us to minimise our reliance on certain inputs such as nitrogen fertilisers and so on. So that's one of the sort of issues there around the environmental costs, the financial costs of nitrogen inputs, and how can you use Earth observation tools in some way to minimise the requirements for nitrogen fertilisers. So that's one part. And then the other element would be the issue about how can we ensure that the productivity growth of our crops continues to grow. Now in that space, if we're to meet food demands by 2050 for a global population, we need to have growth of our broadacre crops in the sort of 2.5% to 3% increase every year, right? Breeders through traditional methods and so on have been doing a great job, but that's tending to sit between 0.5% and 1.5%. So there's a gap between what we've been able to achieve historically and what we need to achieve if we're going to feed the planet. in the decades ahead. So we need to create step changes in the way in which we develop new crop varieties. We also need to create new ways of using nitrogen fertilisers in ways that minimise their use. And we need to be able to better manage that. Now, Earth observation tools are going to provide us some clues for how to do that. The space that we've been operating in terms of a project which is linking the UK and Australia is around focusing on the use of Earth observation tools for looking at complex metabolic traits that can underpin a step change in the productivity of our crops, as well as the way in which those Earth observation tools can get a deeper insight into the way nitrogen is allocated within leaves, so that you can be starting to look for more efficient ways of allocation of nitrogen within key metabolic processes. So one of the key metabolic processes that we need to start selecting for is variation in photosynthetic rates. Right? So photosynthesis underpins life on Earth. Breeders may have inadvertently improved it through time, but they've not had the tools to systematically survey variation in photosynthetic rates at scale. We do know now that if you look at the leaf level, that we can use reflected light as a tool for getting an understanding of photosynthetic capacity. If we create a spectrum of leaf traits which differ in photosynthetic rates and nitrogen concentrations and nitrogen allocation patterns, and we measure those traits destructively, but on every plant we do a hyperspectral reflectance on each of those, we can do machine learning to then train the light against those complex metabolic traits. Brilliant, you can do that now at a leaf level. The problem is that's still too slow, right? We need to start doing it over really large scales, and we need to be able to test the systems in over large numbers of plots. The image you've got on the left there of the national variety trials is a system that the Australian breeders and the GRDC uses for testing performance of plants in a range of different habitats. We need to be able to go to all of those places and actually use Earth observation tools to get deeper insights into how is nitrogen allocated within leaves. How does photosynthetic performance vary in each of those? So leaf level's not going to quite cut it. We're going to have to move towards something which is then allowing us to do it from elevated platforms. We can start with a gantry, which might only be a couple of metres above the canopy. Then we move to drones. We can move then to aeroplanes flying at a mid-height, and then you could go into low or high orbit satellites for that. The sensors that are on those can then provide insights into the chemistry, to a certain extent function, productivity. If you look at the sensors that have been available over the last couple of decades, they've delivered information around, for example, greenness. So you can use relatively simple multispectral sensors for getting an idea of how much chlorophyll, essentially, is present within leaves. And we use that as a bit of a surrogate of nitrogen, but it's not a great indicator necessarily of nitrogen input, and it certainly doesn't tell us about photosynthetic capacity, right? So if the breeders are to have something which gives a deeper insight into photosynthesis and getting to the genetic basis of improvements of that, we need a different type of sensor for that. Now, hyperspectral sensors, which have the ability to, for example, measure reflectance between a really short set of wavelengths of, say, 250 or 350 nanometres up to 2,500 nanometres with lots of intervals along there, that captures an enormous amount of information about the surface of leaves and the underlying chemistry, complex metabolism, so on. And as I said before, we can do that at leaf level. Take that sensor and move it away from the height, from that surface, the fidelity of that degrades. And so your predictability, you're able to predict complex traits at height is problematic once you move away. So the project that we've got with the UK is trying to work out how do we recover the fidelity of complex traits that we know we can do at the leaf level using reflected light, using hyperspectral sensors at height. And so we've been doing that with gantries, we've been doing that with drones, we've got satellite imagery, and we'll be trying to work out, can we recover that fidelity of predictions of complex metabolic traits at height. Early days, in some ways it was a test project to sort of work out what is it that we need to know, what sort of additional work do we need to do, and it's not easy to do. But I think once we succeed in that, and I think it is possible to succeed in that, then the breeders will have a tool which they will be able to go across those national variety trials. They'll be able to look at performance, they'll be able to relate that to photosynthetic activity. It'll also give farmers the ability to actually look at variation in photosynthesis, but also then nitrogen concentrations in their crops in real time, in different paddocks across their fields, and then try to work out in what situations they may need to use different levels of nitrogen fertilisers in those. So there'll be another application into that domain.
Let's take a look at the sustainability conversation now. Richard Lucas, what role does EO play in helping people and nature adapt to climate change and also improve environmental sustainability?
Oh, thank you, and it's great to be here. Thank you very much for the invite. Yeah, I've always, looking at Hugh's images of, I don't know where that was actually, but you look at these sequence of images and they're just images. So one of the things that we feel is that if you can convert those images into information, which is what has been talked about there, but try and do it on a national and international level consistently, that's really quite key. So I'll look at my slide here first of all. It's, we have, fortunately have this in Australia, so you can see those time sequences, and this is produced by Digital Earth Australia, Geoscience Australia. We worked with them to develop this land cover mapping system. And it's available, it's 30-meter resolution across Australia. Those new maps are going to be coming out shortly. But what you see there is like agricultural practices in the first movie at the top. And at the one at the bottom, you see sort of WEPA and mining and so on. So you've got, like, instead of just images, you've got a history. And what we've done here is actually look at taking environmental descriptors, like you could bring in nitrogen, but it's basically things that have units or categories. So it's like meters is a unit, percent, canopy cover, the 12 for the units and so on. Or a category like this is the plant, the crop type, or whatever it is. And what we have is run it through like a global taxonomies, and that's the important part, because at the very top slide you can see we use the Food and Agricultural Land Cover Classification System, and that was developed a long time ago, and often people use about 30 end classes to do that. We actually take all these descriptors, we retrieve them separately from satellite imagery, and we combine them in that framework, which is hierarchical and modular, to produce 12,000 potential classes. Now we have 126 over Australia, but we could actually get a lot more if we wanted to. So that map is not a map, it's all these descriptors stacked together. So that's quite interesting. And the main thing about the FAO land cover classification system is globally applicable. So we've actually applied that. This is where the UK connection comes in. We've applied it in parallel with Australia and Wales in the UK, and it's now going through Switzerland, and we're also putting it through Asia as well. So that's with CSIRO. So that system is quite nice because it tells you about the past, but it doesn't do the blue carbon, the water. So I'll just quickly point that out, but we've also developed going underwater, so you can do corals, seagrass, and so on. So that's the idea behind that. But then you think, I've just got maps of land cover over time, so what does it tell me? How do I get change? So we developed a change frame. I'll come back to your question as well, explain that in the context. So we come up with this change frame that looks at the, using that change over there, the evidence of all the descriptors and the land cover classes to discern the impact. So vegetation dieback, crop damage, flooding, that's the impact, increases in water extent. So that's the sort of things that you see. And you can see, you know, and that's particularly on the second one down, you can see the expansion of the mining and so on through there. So we look at the impact, and then we also can look at use Earth observations to look at the pressures that lead to that change. You know, why did that happen? So it could have been a bushfire, it could have been overgrazing, it could have been too much fertilizer, too little fertilizer. It was all sorts of things. So we've come up with 77 impacts. With each of those, there's 144 pressures, and if you combine them together, you get impact pressures. And you can map those based on evidence from Geoscience Australia's maps, as you can in Wales, and through that system, because it uses global frameworks. So all that land cover, the underwater, the change is all globally applicable. So then we thought about it, and as you can see in those images, you can see the bottom and you think, well, we're always looking at the past. So Hugh was saying, oh, you know, look at deforestation. Well, that happened yesterday. The flooding that's going to happen in Queensland in the next few days. or next week will be yesterday. So we thought, how can you use that to look at what you can do in the future? And it was really interesting being at the previous session here on indigenous values and so on. So what we found is that you can use those same taxonomies, which is where you can help people in nature, because nature is really important, because without nature, people are going to suffer. So what you can do is to use those same technologies to create maps of the future. So we see there's two actual maps there. That's actually from Wales, the one on the top left where it says reimagining it. So it allows you to sort of reimagine what that landscape was like, and you can go back to before the mining and say, well, that's one way of going back, or there could be another way. So you can use those same taxonomies to actually create or imagine future of what you want. And then you can say, well, what do I want by 2030? What do I want by 2050? And you can sort of say, well, you can ask lots of people, and we've got this system where you can actually ask people what they'd like to have. Now, then you have to think, well, what's the value of that future system? So the value is like, is it biodiversity? Is it crop production? Is it building space? Cultural values, whatever it is. What's the value? And biodiversity and so on. And then you have to think, okay, well, we've got the values. You might have 100 visions of that landscape, and you've got the values in there. And then you say, well, what's the risk if this is my future landscape? I know what we sort of have lots of ideas on that. Then you say, what's the risk? And you can use that imagery to work out frequency of fires, frequency of flooding. That was an image just from Ingham last week, a few weeks ago. That's from Sentinel-1. So, we can map the flooding. So we go, it's very annual, we can go sub-annual as well. We don't have to use just one. We can use radar, LiDAR, hyperspectral. We can use whatever we want, because as long as you retrieve the unit or the category, you're fine. And then there's that realization. Is that likely to be, is that realistic, that vision? And with all of that information, because you can't maybe take up Brisbane Airport and bring it back to mangroves, for example. That's not realistic. With all that information, in 2030, there is going to be a landscape. And you can then say, well, how are you going to agree what that landscape is? Either you let it go as people just do their own thing, or you actually have a vision to do that. And what you can do is have that vision with its values, the risk, and all of that, and then you can then say, and there could be values for people and nature, and then you can monitor progress through systems like Geoscience Australia to see if you're achieving what you would like to achieve. So instead of just watching things happen, we tend to do that. The ice melts, CO2 goes up, fires. This provides an opportunity for people to make more sustainable futures, potentially address climate change. How can we be more resilient to climate change? And also, basically, how can we look after people and nature? So hopefully that's a good answer, but I think it's a wonderful way to go forward because it's very positive. It puts a much more positive spin on what we can do. And it's the capability is right here in Australia and in Wales and hopefully other countries too.
Well, the previous session we talked about pests and weeds, massive problem for not only farmers here but also in the UK. How do you use Earth observation to tackle some of those issues?
Yeah, thank you. That's a very nice question. So first of all, thank you, ABARES, for the invitation, and it's a fantastic opportunity for me itself to learn quite a lot. So as we discussed in the last session, so pest and disease is a problem, and the global scale, we lose around 20 to 40% of production due to pest and disease. But also, if something happens, again, this is ABARES statistics, it might take up to $10 billion to clear up a specific pest and disease from this area. So what is key is early detection. So can you detect it as early as possible so that we can contain it within the area and take necessary actions. So Earth observation can apply in number of scales. So you start from what we call the leaf scale to understand how a manifestation of a specific pest and disease might be. So if we look into one of the images on the left, so these are example of what we call leaf scale monitoring. So understanding leaves before it is being completely infested. So you get some. So the ability of Earth observation is you can see things or you can get information about things that we cannot see in a normal kind of eye, in our own eye. So they're part of the technology that will detect various level of infestation. And then you can use that technology to then scale up to other aspects, the canopy level to the landscape level. The other thing that we are using is thermal imaging. So that's, again, something which helps to identify specific signature, and you can take that understanding to leaf level. So we're doing an experiment in the UK where we're looking into a specific virus called the cocoa shoot virus, so which affects the cocoa plant, so and then affects the production later down the line. So what we are doing is we are inoculating a small plant with that specific virus in a controlled environment, and then we are trying to look into it over the time. There is a specific time, how you see the changes happening to the leaves and so on, to give some experiment. Once that is done, then we want to move into monitoring. So the picture in the middle is one of the disease that you might have quite a bit in Australia, the Pythophorus, which is affecting a lot of fruit trees. And again, the idea is we can use technology like drones or maybe a specific satellite sensor to get into that specific signal. But also, we can use automatic machine learning techniques. So the second example here is a red palm a disease which affects palm trees. Like not specific in Australia, but close areas which affect your supply chain. And then, although from a visual point of view, we cannot see a specific differences, using imaging technique, we can see a lot of differences in those. So that helps us with detecting where this is happening. So then the question is then what? We understand what's happening. Then we move to what we call the landscape scale. So this is where we call it modeling. So we understand how to detect it, what's happening, then we monitor it, and then we move to more of a landscape scale for monitoring. The example on the top is locust or fall armyworm. So this is one of the problems here in Australia as well. So what happened is there's a specific pest which kind of eats on your green leaves, and it moves from one place to the other, and quite a big problem certainly in Africa. And how you will help here is to understand what will be the next move, because you identify which areas are affected, but also what are the green areas nearby, and you can understand how this is going to move there. So on predicting where this will go based on the vegetation cover, we can also prepare to kind of cover that. But also the map on the last one on the top right is where we are trying to see which areas are more vulnerable. Like not just predicting where it will be, but understanding those conditions that would make a specific area more vulnerable to a specific pest or disease. So this is where we combine a lot of different Earth observation data sets, so from your SAR data, optical data, or thermal data, to map these areas, most likely to be affected by a specific pest and disease. So then you can get prepared for that later down the line. So it's a range of application depending, like from early detection up to modeling, where Earth observation data can be useful.
So we've heard of all of the benefits of EO. Phil, Tickle, what's needed to improve the adoption of these technologies across the agricultural sector?
All right. Firstly, I'd like to thank you for the honorary doctorate. I haven't got a PhD, sorry, so I'm not Dr. Tickle, I'm Mr. Tickle. But whoever did the slides, so thank you. I can wiggle my arms too, like Mr. Tickle on the cartoon. So I suppose in terms of what CBO Labs does, we were, myself and Dr. Peter Scarth, who does have a PhD, founded CBO Labs in 2018. And that was really on the back of 20 years of frustration in terms of how we as scientists, and I used to be one, but now I sort of manage a heap of people, but really about how we drive the science that's just been described here and drive it to the paddock scale and actually get adoption at the industry and at the paddock scale. So CBO Labs, we're an agricultural data science company, 15 people, about a third of our 5 PhDs in data science and remote sensing, a bunch of database developers and some customer-facing people. But really the key to our business in terms of adoption is how we collaborate with other companies. So I suppose one of the patterns historically in the tech space, there really wasn't an ag tech industry in Australia 10 years ago. In the cropping space, yes, to some degree, but certainly in the grazing and the livestock space, there just wasn't an ag tech industry really at scale. And I think there's a whole range of reasons for that, but certainly in terms of the agricultural industry, that is the least digitised industry actually globally. So in terms of commodity industries, agriculture is the least digitised, and the livestock industry is the least digitised industry of the least digitised industry. So we've clearly got the age profile of producers as well, or farmers, late 50s and higher, and so we've got some generational issues to deal with. So there's a bunch of challenges there. But I suppose I spent 25 years of my career beating my head against a brick wall, trying to drive these sorts of applications to farm scale, and there was always some piece of the technology that was missing. Firstly, it was GPS systems. We didn't know where things were. Okay, and in the early 90s, our GPS systems were only good for a couple of 100 metres, let alone now a few centimetres. We didn't have connectivity, and we didn't have high performance computing. All of these things were getting in our way. So while we had the satellite data progressing, and we had government agencies and universities who had the compute and had the science to bring that technology together, certainly from a private sector perspective, the only organisations that could do that were the big end of town. And the big end of town are very expensive and very slow to really deliver these things. And what's happened over the last 10 years with the advent of cloud computing, obviously Elon Musk has solved the connectivity issue and put NBN to bed effectively. We've solved the connectivity issue, we've solved the compute issue, and as a small business now, there is no limits to our compute, there is no limits to the science, and really it's about then driving how quickly we can drive the adoption. So, we leverage off the science that we've talked about here, and then we're also, we invest in a lot of R&D ourselves. And so the core business for SIBO Labs, we're effectively trying to be the Google traffic for grass, if you like. And so if you think about Google traffic, it wants to get you to the other side of town. You want to know when you're going to get there and how much traffic you're going to go through, whether you've got to take a detour. Our system is really world leading in the space of being able to predict how many kilograms of pasture you have in terms of kilograms of dry matter per hectare you have in every paddock of your farm. On a weekly basis, to literally then push that data straight into a farm management software system that carries information on the number of cattle you've got, run a feed calculator in there and tell you how many grazing days you've got left before you need to move those cattle. So those images on the bottom there, that's an image in central Queensland. Every day they're getting, for that 25,000 hectare farm, at 10 metre resolution, they're seeing the variability in their pasture biomass, their pasture growth, their pasture utilisation in the paddock. They know how they can set a minimum pasture level in terms of residual so they don't overgraze, and it runs a feed calculator and says this is when you've got to move your cattle. Now, we've had examples of one of our customers, for example, he's sitting in Washington, ageing parents that are too old to move the cattle. He's got a manager on the farm, and he does his forage budgeting with SIBO Labs from Washington, and he uses AgriWeb to keep the cattle records, and he rings up the manager and tells them when to move the cattle from Washington. So I think we've, in that space there, that's a good news story. But I suppose that takes us from the paddock scale. What we've also done with Meat and Livestock Australia, we've through a joint industry partnership with MLA, we've built the Australian Feed-Based Monitor, and that's providing information for every single farm in Australia on a weekly basis for free. And in terms of adopting, how do we get producers to adopt it? The first thing is not having a price barrier. So if it's free, okay, that barrier is gone, and then your other problems actually have to be solved. But so we as a business have invested $2.5 million of our own cash, had that matched with MLA, and we're now, every farm in Australia is getting access to free imagery. We've currently got about 5,000 farms covering about 150 million hectares, which is about a third of the grazed area, using that service. And the paddock level service, we've got about 50 million hectares of farmers actually using that on a weekly basis, and growing at about 50% a year. So that really is tactical decisions, and at the industry level to have the whole nation covered, which is what government agencies used to do a lot of. And that map on the top right there, for example, that you're seeing, we talk about, and there's been a lot of conversation here about weather, and so what we're showing here is a pasture anomaly map. So one of the things that people know about is rainfall deciles. So everyone here probably knows what a rainfall decile is, and if it's in the third decile, it says you're only getting about 30% of your rainfall for that month. Well, it doesn't tell you anything about the effective rainfall. It just tells you that you had that much rain over the month. It doesn't tell you whether it's 100 mils that have fallen in an hour or a week. So what it's actually really is about is the effective rainfall, and that map on the top right there is a pasture percentile map, and the brown areas are showing that lowest 20th percent of pasture growth for the month of March since 2017. So that's effectively your drought map rather than a rainfall map, basically. So I suppose in terms of, just to skip forward just to one more step, so this is really about how we actually provide information directly to producers. The other element there as well, just in terms of the adoption, I'm going to come back to how we bring these things together. The other element here, we've heard a lot about our social licence to operate, regulations in the room here in the last 2 days. And typically one of the barriers to adoption of these technologies by farmers is firstly they don't know how to use it, they're not aware of it. But second, the third element there is the big brother that's watching us, and there is a great fear from individual farmers about who's watching them. They're inherently a private community, if you like, and so what we're doing as a business is flipping the thing around, and we're not the regulator. We are a private organisation working on their behalf to tell their story. And a big part of this, I suppose, we've heard lots of talk about social licence to operate, and we see lots of images every day. I come from a farm myself. The family walking across the paddock, and the sun setting, and we're doing a good job. We've been here generationally. We know our land. We know it better than anyone. Just trust us and leave us alone. Okay, that doesn't cut it in the market today. And we actually have to prove that we are doing the right thing. And so one of the most, I suppose, challenging ones recently, the European Union deforestation-free beef regulations that have come in, lots of politics, lots of people up in arms that how dare another country, let alone a market, tell us what to do. We've built a system to solve that, where an individual producer, they register into the system, we do the detection of the deforestation, we go to the farm scale, we actually then contact the individual producer, get them to provide evidence back to us. Remember, we are actually operating on their behalf here. We're not a policeman. We're actually on their behalf to prove their environmental credentials. They can then, they request the service, we map their property, we detect the change against the baselines and the definitions, we go back to the farm and get other evidence if we require it to verify what's happening on the ground, and then we can slide that into the supply chain quite seamlessly and privately. And on that graph as you're looking in there, as we go from the right to the left, we're at the farm on the right-hand side. On the left-hand side, we've got a processor. That information, the credentials, can be attached to an individual farm. It can be attached to an animal consignment, and then it can be attached to individual animals to go down the supply chain. So we have the ability now to attach a credential, whether it's an emissions intensity report or a deforestation status or any other credential, to individual animals. And as they're going into the supply chains and into the processing facilities, we can then track the provenance of those animals. So we now have the proof to the market to actually demonstrate that we actually are sustainable. It's not just a story anymore.
How do we get closer collaboration between private service providers, from universities, researchers, academics, to help improve the climate change scenario or climate change crisis, and to make these farming systems more resilient by anticipating droughts and patterns? Can anyone speak to that using EO?
Look, I suppose just in terms of just leading off where I came from a minute ago, the first thing, we've actually got to get it used, I suppose. We have to have it adopted, and clearly there's a lot of adoption of the technology at the government end, at the academic end. Australia's got world-leading scientists in terms of what we're doing in terms of the science. The challenge is actually how you get it to the farm and have an impact. And whether it's a supply chain, an individual farmer or a retailer, there's in that supply chain I was showing you there, there's value all along that supply chain. So we as a business, we're all refugees of government agencies and research agencies. So I used to work for CSIRO back in the day, early years. I worked for Geoscience Australia. We rely as a business, we rely on government and universities training the people in those skills, and then obviously we've got to do a bit of retraining when they come to us with some of their habits maybe. But look, in terms of there's like the underpinning science has got to be built through very strong academic sort of roots, but then it's really about collaboration there. So that pattern of trying to do everything yourself no longer works. Big organisations, big and slow organisations that try to do everything themselves will fail in today's environment. And I suppose whether it's research or whether it's application development or whether it's commercialisation, there's not any single piece of technology that will solve the problem for an individual producer or a business. So what we have to do is be the best at what we do, and then team up with other companies to then provide combined services to those farms in a really easy to use way, where they can just click the button like Google Traffic, if you like, and get an answer. So I think that's really changing in the last 5 or 10 years is the pattern of collaboration, and anyone that doesn't collaborate in the ag tech space will fail.
How are farmers adopting this technology in the UK?
Well, just quickly to answer, the first question about the pick and adoption, I think for me, there's two main issues and challenges and potentially opportunities. The first one, I think, is in the training side, right? And it's not just training the scientists and potentially farmers to use the data and to trust the data. It's actually, from a policy perspective, the government officials needing to know that A, this kind of data exists, B, how to use it, and see what the limitations and benefits are of adopting it and using it more frequently. And the second thing is the end-to-end system, right? So we think of satellites as big, expensive bits of kit out there, and they just produce pretty images, and right, I like showing those pretty images. But actually, it's valuable data. But again, you can't take that data alone. There's very few instances of Earth observation data being the sole solution for a problem. I mean, potentially monitoring methane leaks is one thing you can do. Monitoring how much heat is being given off from your roof, potentially another way of directly using satellites. Mostly, you have to integrate them to complex models, assimilate the data, process it so it becomes useful, and then turn that into actionable, intelligible insights. It's an end-to-end chain that involves very complex, satellites through to information and kind of on-ground validation, people who know the system on the ground. It's a complex system. So thinking about it as an end-to-end system, employing basically the same kind of techniques that CBEL Labs are doing and using the tools and the mechanisms that we have available to us, so then it does become, to answer the second question, useful for the farmer. I mean, the farmer doesn't really care about, in the end, kind of hyperspectral images. They don't really care about land change use. They may historically be interested, but they probably know how their farm has changed over the years because they lived it. So actually, when it comes to it, useful data that the farmers can then turn that, data sets into productivity, and then doing so on a way that's sustainable. Because I don't think many farmers would ever say that they wanted to just rape the land of its natural resources. They want to do so and benefit the environments. And that by itself is working to address some of the climate change policy areas.
Jadu?
Yeah, can I just add on to that? I think that's a very good point. And then also it's co-development. So this is what is not happening, or we are seeing a little bit of this happening, is co-development with the end user. So rather than we developing a product and taking it to farmer and say, is it useful, or then explaining what it is, you flip it upside down. You go to them first and say, what information do you need? And then for us, as a scientist or researcher, to find out if we can convert Earth observation data into that specific information. And that will help in terms of adaptation. But another aspect is having from this end-to-end solution, but also the government initiative, like in Europe, we have the Copernicus system, and which is probably one of the good examples of how Earth observation can be utilized in any downstream product. And this is where you not only develop solution at level of satellite sensors, but also think about the usability and kind of try to encourage businesses or commercial organizations or research organizations to develop something that has market value in it. So you develop the whole ecosystem of the technology from launching up to the application. So that will also help in terms of promoting them.
Richard, did you have something?
I was just going to say, one of the nice things about your system is, we found this as well, is to make it freely available initially, because I think often if you've got to pay for it straight off, the uptake isn't there. So I think that's where I feel that in the UK and in Australia, you know, it makes a big difference. The other thing is that there is so much information out there that we often find that farmers just can't comprehend it, and that's too much. And so trying to break it down to simple units and whatever, you know, simple language really is, and that's what we use, and I think that's what Phil is also using as well, is really useful. But also I think in terms of sustainability and resilience, it's like trying to understand what else I could do, and what does sustainability mean, and is there another way of using my land, or can I use my land to be more productive but also give some room for that resilience to step in. We've been up to Queensland last year and last week actually, and you can see it's starting to get a bit trashed, we know, with fires and floods and things, and you can see that might keep on happening, and so it seems to me that resilience into that landscape is really critical. It's quite surprising. You've got, you know, the heavy storms, another one coming, as I said, coral bleaching, you've got, you know, the fires down south, which Hugh showed, and that's not normal. And you can see the environment's degrading. And so you need to build that resilience, but also I think agriculture, you still need to keep the production. So it's this balance about what's happening, but there's get to the point where it becomes so unresilient that you're starting to get real damage like erosion. You're seeing that already. So I think trying to simplify it for people, and like CBLA is really commendable, to be honest. I think it's really good the way they've done that.
Owen, would you like to add to that?
It was in relation to the collaboration part. And I think Hugh had mentioned the fact that Earth observation is just one part. You've got to have ground truthing. There's got to be a whole bunch of other elements. It's just one aspect in your toolkit, right? And if you're going to have collaboration, making best use of the research capabilities of our university sector, we've got to find a different way of connecting to someone who understands sensors, who might be in a department of astronomy or something like that. There might be someone in a department of computer science that's really good at machine learning. Then there could be someone that could be in the phenomics space or understanding biology and so on. And that's really hard. How do you bring together all these disparate people that might be able to deal with a problem that MLA's brought or the GRDC's brought or whatever, which has applications of Earth observation tools? So I think we need to be mindful that it isn't straightforward to make use of that wonderful resource that sits within universities. At the ANU, the reason why we have innovation institutes is that one-stop shop, right? It's how does that complex problem come into a space that says, right, I need 4 or 5 different capabilities. I don't have them in my company. You have them there, but can you facilitate the conversation with those people to design the work that needs to be done to deal with the problem, right?
And what is the crossover like between private and public? Is there much collaboration in that space?
You know, at the moment, so I suppose comment there, at the moment, you know, as a small business, we've got about $15 million worth of R&D projects that we're involved with at the moment, which have multiple universities and then other companies involved with that. So it is happening. Certainly, Food Agility, CRC, who we do a lot of work with, there has been in the past significant issues around IP and managing the IP from research organisations and government organisations, and I suppose what we've and you know, into the private sector and to how to commercialise that IP. We've been able to navigate in recent years, and certainly within Food Agility as an example there, there's research being done and from an IP perspective we have a very clear definition of that the universities and the academic space get full access to all of the data. They've had more data than they've ever had before because we've got private companies like ourselves on the ground collecting data on the ground and giving it to them, and rather than them having to go out in the field all the time. Complete freedom to operate, to do the research and to publish that research, and then now we have the ability to take that IP and drive it straight into commercialisation. So it has reduced the gap immensely in terms of having that collaboration model and the IP model, and for us to have no barriers to drive that commercialisation. But the biggest barrier for us and in this whole space is it's not other companies, it's lack of awareness. Farmers just don't know that you can do this stuff. and until their kid comes home from school and maybe shows them something. They don't open their emails. They don't read the newsletters from Meat and Livestock Australia or GRDC. And so we've got a really big education challenge. And so, I mean, what better platform to teach mathematics and science than this stuff? There is any career that you want, you can have it in agriculture. If you want to be a data scientist or a physicist or a marketer, you can do it in agriculture. And we've I suppose, coming right back to the high schools and agriculture falling away in high schools, they should be teaching mathematics through their school farm, ultimately, or whatever it is, and driving that into the universities. We're also finding at the moment within the tech space, in terms of taking information home, quite a few of the agricultural universities in particular really aren't doing a lot with the ag tech space. They're doing a lot of in the plant science and animal science, but not doing enough in the ag tech, so we're hoping to influence that. Yeah, look, I think, but ultimately the comments earlier on around the, in the time that I've been in this space, so I was 10 years before CBAR Labs working in this space, trying to work out how to solve the problem, and then decided to quit my job and solve the problem. And so those barriers that have been taken away now, but I've never seen more change in the agricultural sector than we've seen in the last decade, whether it's the technology or the markets, and so it's really quite confusing for most producers trying to keep up with it, and they want simple solutions. So we turn terabytes of data every day into a single number that just says how many kilograms of pasture you've got in your paddock every week. That's the number, and whether it's green or brown. It's taken us terabytes and supercomputers to get there, but it's just two numbers to get there.
Hugh, you're a science communicator. How do you get that message through, perhaps to the next generation? It's the younger farmers that love adopting technology.
I also think that, so I'm a science communicator, I think setting up these international programs are a privilege. And we're going over to other countries, seeing how how you will run your own systems, your funding systems, how you bring people together. And I think that's a really interesting perspective, because we sit within our own siloed perspective of this is how you must do funding, this is how you must do your education. That actually it's the combination, it's the powerful combination of bringing collaborative partnerships internationally, interdisciplinary, that you actually start to bring some really exciting answers and conclusions. And you sit there in a lab, I'm a laboratory scientist, not realizing actually out there is a solution, out there is a challenge, there's a problem that you could potentially solve. So it's getting out there and actually seeing what the challenges are is one of the biggest benefits of A, these international collaborative projects, and B, working across interdisciplinary space. And they're exciting, right? These are real world challenges, and that's what inspires people, not just the theoretical side. And what we're seeing here through the academic links is actually there are real world solutions to the work that you're doing, and there will be high impact stuff, like the stuff that Richard is doing, national scale adoption across a nation. Well, Wales is actually putting a lot of investment into the stuff that Richard's doing. The challenges that Owen's looking at, fundamentally, it's a big scaling challenge, right? Going from leaf level to planet level, and then what you can do with that data set is super exciting. That's how you're going to encourage the next generation of researchers, farmers to adopt, is by giving those exciting opportunities.
What about money? Who's funding all of this? Are the universities interested in giving you more money to do what you do?
Well, from my perspective, it was interesting with the previous session, you have a vision, and the vision was always to do Australia and Wales and put it together, have that single vision and don't move from it. And then you accumulate funding to do that vision. So that's the one thing is don't do a project over here that's different from that one, but have that vision that goes forward, and it sort of gathers. It's like a rolling stone. Doesn't gather moss, it gets snowball. So yeah, that's one way. And then funding is always a challenge, and sometimes it's really frustrating, because you often get, often when you develop something, the funding then dries up because it's done, but it's not done because you've still got to climb it. And it has to keep on going. And it's often the case, you develop something and then it drops. So, and that's frustrating. Yeah.
can I add on to that funding? I think one of the things that we also struggle at the university sector is taking things to market. Like we keep it at the research level, and now making it more operationalization or taking it to people is where that industry and university collaboration comes in. So there are two levels. Like either there's limited exposure of academics to work into that space because that's a different space. Commercialization is a completely different space. And also there is, although there are incentives from different governments to help with that space, but it's not properly, like educated to the community. So I believe more effort to bring more industry and university together would help with some of those funding issues that we have, and may strengthen and help, help to take things from research to market, and that would benefit everybody.
Yep. So now, from a commercial perspective, as I said earlier on, we have a pretty large research portfolio. We're putting about $1 million a year into R&D ourselves in terms of real people doing work as well as cash. But obviously leveraging off other CRC sort of environments as well. But I think the other element here is, and we as a business, we've never taken any venture capital. We've taken a $50,000 grant in 8 years. That's it, and everything else has been built on whatever we can earn. And I suppose what we're relying on is if you get people to pay for things, they value what you do. And so that's sort of an element of a producer. So yes, we need to give things, the freemium model like we do with everything, and to give people a taste and see if there's value in it. But we also see that, particularly at the agricultural level, when people don't pay for things, they don't fully value it either. So there's a bit of a sort of a tension there. But what we're also seeing, particularly in the last 5 years, the growth of, as a comment earlier on I made around, in the past we had regulations that were, controlling tree clearing in Australia, for example. Now the state government regulations are largely, I won't say irrelevant, but we've now got the markets saying that they actually need to be deforestation free. So we've now got the whether it's the EUDR, which people aren't very happy with, but we know for a fact that most Australian producers won't have an issue. You just got to prove it. We've now got things like the Science Based Targets Initiative, the Accountability Framework, the nature-related financial disclosures. So we've now got 10,000 big companies signing up to SBTI. We've got the banks, we've got the processors, we've got the retailers signing up to these various market structures. What that then means is that the likes of a McDonald's require the producer to give them information to help them solve their Scope 3 emissions problems. All the processors, all the retailers need to do that. And so what that then means is that the retailers and the processors, and effectively anyone in that value chain, now is reliant on the farmer giving them information to help them solve their reporting problems at a reasonable granular level. They can do it through industry averages, which is what they do now, but ultimately it's going to be at the farm level. And so what we're sort of gradually moving towards is trying to architect effectively a smart contracts model where a ledger can be stored, and some people call it a blockchain. But in the future, we can see something that we might charge a farmer $1,000, for example, for them to use it. Well, as they give it to their processor, and then to the retailer, and then to others and then their bank, who all get value out of it, each one of those beneficiaries of that information should be paying for some of that. And so I'm really hoping in the future that that's going to be the norm. And I suppose we've got some small examples of that now, where a meat processor we've got a coupon code. The meat processor has given that coupon code to their supply chain, and they can get a free Seabird Labs service just using their coupon code. So that's one example, but we've now got multiple people in these supply chains that should be paying for the information that they actually get from the farmer.
I think related to a lot of the issues we're talking to here, though, is the accumulation of massive amounts of data. In our own experience around linking any Earth observation technology through to an application has been working out how do you bring disparate forms of data together in a way that you can interrogate collectively, particularly from an AI perspective. And so if you were to go, for example, to the Australian Plant Phenomics Network that's just gone national in the last 12 months or so, one of the biggest challenges they will have as they expand their capacity to non-invasively monitor remotely a range of traits related to plant performance and so on, is how do you combine environmental data with hyperspectral data, with plant physiological data that might have been emerging in a way that be collectively interrogated. It isn't easy to do.
And
so
that
really,
farmers understand.
yeah. And so whilst it's terrific, actually, I think, from the point of view of a private business, being able to construct a model which is predictive and it's giving real tools to use is great. But we've got to work out the equivalent of that in some of these other domains, massive bottlenecks. And the risk is a real risk. You collect the data and you don't know what to do with it because you've got no way of collectively interrogating it.
Richard Lucas.
Yeah, no, one of the solution we have is these, and I hadn't really realised how important that is having global, I said up on the screen, global taxonomies that use consistent units and categories, and then you can classify everything. I can classify that table, and I can classify 1,000 years ago, I can classify 1,000 years into the future, I can classify Mars, and all of the evidence for those units and categories builds up to the impacts and the pressures. So I can look at, weed invasive plants, you can look at, the pasture biomass in kilograms. As long as you've got those units and categories and it all fits together, then you can start talking to each other. And I think that's my solution to the saying, because I think it works. Well, I know it works, and I can go underwater. So I think that's the way to go.
Now, maybe we should open up the panel. Does anyone in the audience have a question for our panellists?
No?
Come on here.
Great discussion. A question. How can VA data improve the accuracy of long-term climate models and early warning systems?
I can.
Yeah.
Yep, I can.
I'm on the screen.
Yeah, thank you. Yeah, I can answer that a little bit.
Maybe repeat the
but
question too.
There'll be lots of other.
Yeah. You go on then.
Yeah, so we work with the ESA Climate Change Initiative, and one of the things that we do biomass globally. A lot of the climate models are predicting biomass, but they never had the biomass estimates in which to validate the models. So, but now they do, and because we've got time, you've got like 10 years of annual biomass globally, and so the models predict it, and so we can improve the modelling because of that, because it's not right for the Amazon, it's not right for Australia. So that's one way that I would say. ProfJadu.
Yeah, so one thing I would say for climate model, you need a longer term data set to calibrate and validate that. And one of the key challenges once you have a longer term data set, because of the technology, you have multiple missions going forward, getting data set from that. And making sure that they're accurate and the uncertainty is less is quite important. So one of the steps that is happening in the UK, led by the UK mission called Truths. So it's a sensor that is being launched in a few years' time, where it would provide a calibration for all other satellite sensors. So it would be a lab in the space. And what that would ensure is all missions are calibrated to the standard that you can traceable going back to climate model. And that would be a step change in kind of improving the accuracy of the. It's called Truth. So T-R-U, like truth and S at the end. So it's a new mission. It's being led by UK, but funded by European Space Agency. So will be used to, it's a gold standard calibration for any kind of satellite observations that is mostly in the optical domain. And that will change quite a lot, yeah.
Owen, you've got something to add.
If you think of climate modelling, not necessarily weather, but around predicting how hot the planet will be in the coming decades, in order to do that, you need to know how much atmospheric CO2 will accumulate and the forcing that will create and the amount of temperature that will build up on the planet. In order to do that around prediction of atmospheric CO2, you need to be able to model carbon exchange between forests and the atmosphere. The biggest uncertainties in the dynamic vegetation models that are coupled to those climate models is the temperature response of those carbon exchange processes between vegetation, soil and so on, and the atmosphere. So the Earth observation tools will allow us to narrow that uncertainty in the way in which those processes of carbon exchange occur. We do it at the moment very, very slowly, plant by plant, and we build up. And we need Earth observation things to do it temporally, spatially, much more thoroughly in order to be able to narrow that uncertainty.
Yes, there's a mismatch of scale there. You're talking about leaf-based processes versus trying to capture something at 50 metres resolution. But that was, my question was more general.
Yeah.
To do with, we've seen a lot of, a few sessions here that have looked at different forecasting models, agricultural commodities, for example. My question was more general, how Earth observation can make those forecasts more accurate. So, for example, with wheat forecasts for the coming season, livestock production.
I would also say that it's doing that now.
Yeah.
That's Earth observation underpins our climate data
So
records.
you mean in terms of initialising models, benchmarking,
Yeah. And I think there are limitations in our computational power at the moment. So it's not an Earth observation issue. It's a computational supercomputing issue. It's expensive to run. It takes a lot of time and effort on these supercomputers. But I think it's two-thirds of all climate data records are underpinned by Earth observation data. But you're right, it can get better, and I think the data bottlenecks of bringing in other data sets to help support that, fusing those data are always just going to make it more and more accurate going forward.
Can I just add on to you mentioned our crop model, and I think this is where there is the biggest opportunity in terms of integrating Earth observation, because the communities are quite different, so the crop model works at quite detailed characterization scale, whereas Earth observation tends to generalize those kind of responses using indirect indicators. So I think that's another bridge. Yeah, so we need to cross that. Is the definitions we get from Earth observation are mostly indirect. So translating that indirect information to something that is useful for the crop model is really important, and work is being done. And one of the projects that is within this program is where we are trying to look into different Earth observation input. How can you use those in crop models? And we'll come out with some recommendation where it can be used to scale that up.
Got a question online. How do we create rural R&D systems that integrates the realms of science to enable the connections required to fully benefit from information available via EO? It's a deep one.
So just say that again.
Say it again. Summarise it.
How do we create a rural R&D system that integrates the realms of science to enable the connections required to fully benefit from information available via EO?
Yeah. I suppose I'll probably just give you a snapshot. Right now, we're talking to a number of industry bodies and processors, as in meat processors, around supply chains, and even the simple thing like there's a local drought in northern New South Wales, or in the case southern New South Wales at the moment, the impact, the knock-on that has on animal prices when people have made decisions too late. They're selling off. They're driving themselves into sale yards, dropping prices. You then have knock-on effects into the abattoirs when you've got the abattoirs being loaded up without workforces. All of these things are very, very front and centre for these supply chains now, and so we are seeing the need right now, having conversations around how we link our data to forecasting animal weight gain, when they're going to be turned off, are they going to be coming in early, what impact that's going to be having on a workforce in a rural abattoir, for example. Right through those communities. I think bringing all this information together, it's not just one piece of information, it's these very, very well integrated models will actually then help drive local labour forces, for example.
Maybe one comment from each of the panellists before we wrap up this session. What do you see coming in terms of the ability to adopt this technology? What's in the pipeline? What's the potential that we haven't harnessed yet as an industry and as researchers?
I think that's the $64 million question, right? I mean, that's the reason we're going out and getting programmatic funding from governments, and that's kind of our job, is to get these funding together so we can offer the opportunities to solve, to come up with these solutions that you guys are driving, right? That there are problems in the community, and we have solutions in the academic and industrial communities. We need to bring those together to solve them. But it's exactly what we're working towards.
And for me, the important part is making sure that we do our homework of understanding the needs of stakeholders. So that, yes, you've got a voice for farmers, producers, and people that are in the intermediate sort of elements, might be in your RDCs, and find a better way of connecting all of those needs to the research capability that we have in the nation, which is not being appropriately harnessed at the moment, right? I think we're not harnessing in a way that's ultimately having as big effect in the real world as we need to. So for me, I think going forward is one of the primary things is better ways of connecting all our different disciplines within the university sector to those needs where EO, Earth observation tools, could be providing solutions. That's going to require us to bring together a whole bunch of different disciplines.
I think we have this reliance, which is forgotten in many ways, on nature, and with resilience and things like pollinators and these sort of things, we're seeing, reductions in biodiversity, the climate change impacts, and so on. So I would use the past to just focus on what you can do in the future and really try to plan a lot more to make sure that we don't continue on the path, because it's not a good path. And so I think proactively use that data that you've had all over that time to say, we can use that to say, this is not going to burn, this is how we stop burning. And a little bit like with Phil, is just saying then, you're like, what caused the loss of productivity in stock? Or why did I make that mistake? And try and do it, but also put nature as priority, and that's very much, I think you should do that.
I think as a community, we should work towards increasing trust in the Earth observation data and the information that you provide. And that can always be work together with the farmers, so kind of working with them, how reliable the information that you're providing, so trust. The second one is openness. So make it open as much as possible so that they can see what's happening with the data set and how the information is being produced. So hopefully that will help to uptake, all this into.
Phil, where do you see things going?
I think there's no doubt enormous technological change, and we need to be investing in that and driving it. I think what we're seeing at the moment is the activation of the supply chains, and where producers have historically been price takers, not price makers. And they've been disempowered by effectively others in the supply chains and the value chains. Producers, through market mechanisms, it won't be regulation in 10 years' time that's actually stopping producers from doing things. It'll be the market specifications that they have to meet to get access to that market. It mightn't necessarily be premiums. It's just getting access to that market. So, the big shift then is those supply chains are going to have to help farmers get there, and they're going to have to help farmers pay for it.
Hugh Mortimer, Owen Atkin, Richard Lucas, ProfJadu Dash and Phil Tickle, thank you for sharing your insights at ABARES in 2025. Please thank our panel.